In this video, we're going to talk about the twin paradox and how to calculate the proper time along curved world lines using the Minkowski and Rindler metric tensor matrices. Let's start with the twin paradox. The twin paradox involves two observers, Alice, who stays home on Earth, and Bob, who goes on a round-trip journey on a rocket close to the speed of light. Some people will argue that, since special relativity tells us that moving clocks run slow, Alice will see Bob's clock tick more slowly than her own clock. This means that when Bob arrives back home on Earth and compares his clock with Alice, Bob's clock will have counted less time than Alice's clock. The argument continues that in special relativity, since everything is relative, all frames of reference are equally valid. Therefore, we can also view this situation as Bob's rocket being stationary, and Alice and the Earth going on a round trip relative to Bob. In this case, Alice's moving clock ticks more slowly than Bob's clock, and when they compare clocks, Alice's clock will have counted less time than Bob's clock. The argument goes that this is a contradiction that disproves special relativity. This argument turns out to be wrong. And the key mistake is assuming all reference frames are equivalent. Special relativity does not say this. It only says that all inertial frames are equivalent. And in the twin paradox scenario, at least one of the two frames must be non-inertial, and so the frames are not equivalent to each other. To understand why the twin paradox is incorrect, we need to understand how to calculate proper time. In Relativity 104 Part E, we learned about the proper time tau, which is the time measured on a clock that's traveling with the observer. We started with the four-position spacetime vector S, which indicates a position in spacetime. Then we defined the Minkowski metric, which says that for inertial frames, the dot product of the time basis vector with itself is +1. And the dot products of a space basis vector with itself is -1, and the mixed basis dot products are 0. From there, we defined the spacetime interval, s squared, which is s dot s, which in inertial frames is ct squared minus x squared minus y squared minus z squared. We said that a vector was time-like when s squared was greater than 0, and for time-like vectors, s is the speed of light c times the proper time tau. This is also called the vector's Minkowski length because it is calculated with the Minkowski metric. In this video, you will hear me call tau the proper time, but sometimes I will also call c times tau the proper time. Tau is the proper time measured in time units, like seconds, and c times tau is the proper time measured using space units, like meters. To measure a time in meters, we just measure how long it takes for a beam of light to travel that number of meters. So if we assume the y and z coordinates are 0, the four-position vector only has time and x components. If we want to know how much proper time goes by on this world line between these two event points, we just get the components of the four-position vector using our spacetime basis. To build this four-position vector, we need 5 time basis vectors and 3 x basis vectors. And plugging the components 5 and 3 into our formula for proper time, we get that c times tau is equal to 4. Now, let's say that we have an observer that travels to the right, then stands still, then travels left, and then stands still again. The world line for this observer is not a straight line. So how do we figure out how much proper time has passed on a clock that's traveling on this world line? We can find the total proper time just by adding up the proper times for each individual linear segment of the world line. The first segment is given by the vector s1, which is 4 time units and 3 space units to the right. The second segment, s2, is 2 time units and 0 space units. The third segment, s3, is 2 time units and 1 space unit to the left. and the last segment, S4, is 1 time unit and 0 space units. For S1, the time component is 4, and the x component is 3. So the proper time c times tau equals the square root of 4 squared minus 3 squared. This is the square root of 16 minus 9, or just the square root of 7. For S2, we can read c times tau equals 2 directly from the time component of the vector, since the vector has 0 space components and therefore no time dilation happens to the proper time. For S3, the components are 2 and -1, so c times tau ends up being just the square root of 3. And again, for S4, we can read c times tau equals 1 directly from the time component, since the space components are 0. If we add up all these proper times together, we get the square root of 7 plus 2 plus the square root of 3 plus 1, which ends up being about 7.38. So we've calculated the total proper time along this non-straight world line just by adding up the individual proper times for each segment. We can also apply this technique for our twins in the twin paradox scenario. Alice stays home on Earth, and so she has a straight vertical world line, which we can represent by the vector SA, which is 6 time units long and 0 space units long. Bob does a there and back journey on his rocket ship, so his world line through space-time is a combination of 2 linear segments, given by the vectors SB1 and SB2. SB1 equals 3 time units and positive 2 space units, moving to the right, and SB2 equals 3 time units and negative 2 space units, moving to the left. Using our formula for proper time, it's not hard to see that Alice's proper time is just 6. c times tau is just 6. And if we calculate the proper time for the 2 segments of Bob's world line, we get the square root of 5 plus the square root of 5, which is about 4.47. So given these results, we find that Alice's total proper time of 6 is actually greater than Bob's total proper time of 4.47. So even though Alice and Bob start and end their journeys at the same points in space-time, Bob actually experiences less proper time overall than Alice. So this is a very important concept to understand in special relativity. Proper time doesn't just depend on the start point and end points of a world line. The proper time also depends on the path you take through space-time. In some ways, this is similar to physical space. In New York City, on the island of Manhattan, most roads are arranged on a grid. But there's one street called St. Nicholas Avenue that runs diagonally through the grid. It should be common sense to us that traveling along the streets in the main grid, along vector B1 and then along vector B2, will give us a different distance than traveling diagonally along the vector A, which is the vector sum of B1 and B2. The total length of the vectors B1 and B2 is actually longer than the length of the vector A. Mathematically, this is stated as the length of B1 plus the length of B2 is greater than or equal to the length of A, where A is just the vector sum of B1 and B2. This is called the triangle inequality. It basically means that the lengths of any 2 sides of a triangle added together will always be longer than the third side. We have a similar situation in space-time, with Alice's straight world line and Bob's zigzag world line. Traveling along Bob's world line, along vectors SB1 and then SB2, will give us a different proper time than traveling along Alice's world line, SA, which is just the vector addition of SB1 and SB2. Except now, there's a key difference. Traveling along SB1 then SB2 actually gives us a shorter proper time than traveling along SA. So the Minkowski length of SB1 plus the Minkowski length of SB2 is actually less than or equal to the Minkowski length of SA, which is the vector sum of SB1 and SB2. This is the reversed triangle inequality, where the inequality sign is the opposite of the sign we saw for the triangle inequality in physical space. This inequality only applies for time-like vectors, which are vectors that are more vertical than the world lines of light beams in a space-time diagram. So in physical space, the triangle inequality tells us that when we have two vectors, b1 and b2, and add them together to give a third vector, a equals b1 plus b2, then the sums of the lengths of b1 and b2 will always be equal to or greater than the length of a equals b1 plus b2. This basically means that a straight line is always the shortest distance between 2 points. Any zigzagging we do will make the path longer. But in spacetime, it's the opposite. The sum of the Minkowski length of time-like 4 vectors, SB1 and SB2, will always be smaller than the Minkowski length of the sum of the vectors. This basically means that in an inertial frame, a straight line between 2 points will have the longest possible proper time between those 2 points, and that doing a zigzag will actually decrease the proper time between the points. So coming back to our twin paradox, the fact that Bob experiences less proper time than Alice makes sense if we accept the idea that a straight line between points in spacetime will always have the longest possible proper time in inertial frames, and that doing a zigzag path will actually decrease the proper time. Now, in the twin paradox, some people will claim that the situation of Alice standing stationary on Earth and Bob doing a there and back journey is completely equivalent to a reference frame where Bob is stationary and Alice is moving on a there and back journey, meaning Bob now has the straight line path that takes the longer time. And supposedly this contradiction proves that special relativity is inconsistent. But this line of reasoning is not correct. If we assume Alice's world line is inertial, then Bob's world line is non-inertial, because he will experience a fictitious force when he changes direction. This makes Bob's world line fundamentally different than Alice's inertial world line. Recall that the first postulate of special relativity says that the laws of physics are the same in all inertial reference frames. This basically means that all inertial frames are equivalent to one another. And remember, we use Lorentz transformations to switch from one inertial frame to another. Anytime we have an inertial spacetime basis, which is a Minkowski orthonormal basis, we can always change to another inertial spacetime basis using a Lorentz transformation. So if Alice has a straight world line that's stationary in space, and Bob also has a straight inertial world line that's moving to the right, it's possible to use a Lorentz transformation to make Bob's world line look stationary like Alice's, where Alice looks like she's moving to the left. A Lorentz transformation can change straight lines into straight lines on a spacetime diagram. But if Bob has a there and back zigzag-shaped world line, it's impossible to use a Lorentz transformation to change it into a straight inertial line, like Alice's. A Lorentz transformation cannot change a zigzag into a straight line. So the resolution of the twin paradox is that if Alice's frame is inertial, then Bob's frame must be not inertial. And these are fundamentally different in special relativity because we cannot make Bob's world line look like Alice's using a Lorentz transformation. It's perfectly fine that Bob's clock measures less time than Alice's. Now that we've resolved the twin paradox, the next thing I'll do in this video is show how to calculate the proper time along a curved world line in a given coordinate system. The key to calculating proper time is the metric tensor. specifically the Minkowski metric in inertial coordinates and the Rindler metric in Rindler coordinates. In my tensor calculus videos 11 and 12, I show how to get the physical length of a curve in physical space by approximating the curve as a series of straight lines and adding up the lengths of these lines. Let's say that a curve is given by a position vector r that moves around in space based on a parameter lambda. To get the length of a line segment, we take the position vector at the start, r of lambda, and the position vector at the end, r of lambda plus delta lambda, then subtract the vectors, and then calculate the length of the resulting vector, and then sum up the lengths of each segment vector to approximate the curve's length. Here, delta lambda represents the spacing between the endpoints of the line segments. If we multiply and divide the lengths by delta lambda and take the limit as the spacing between the endpoints gets smaller and smaller, our sum becomes an integral, and this difference vector over delta lambda becomes the tangent vector dr by d lambda. So the key to calculating the physical lengths of curves is knowing the lengths of the curve's tangent vectors, which we can calculate using the metric. To see this explained in greater detail, check the description for links to the tensor calculus videos 11 and 12. It turns out that, in space-time, we can also calculate the total proper time along a curved world line by approximating the curve as a series of straight world lines. We take space-time position vectors for all the world line endpoints, subtract them in pairs to get the difference vectors, and then sum up the Minkowski lengths of all the world line segments to approximate the total proper time on the world line. To get the exact proper time value, we take the limit as the spacing of the endpoints goes to 0. We get an integral of the Minkowski length of the tangent vector ds by d lambda times d lambda. Also, I just want to point out that the world line's tangent vector ds by d lambda is not the same thing as the world line's four-velocity vector ds by d tau. The four-velocity vector ds by d tau always has a Minkowski length of c, but a generic tangent vector ds by d lambda can have any Minkowski length. The two vectors are related by the single variable chain rule using d tau by d lambda. So the key to calculating proper time along curves is getting the Minkowski length of the tangent vector ds by d lambda. And the length of the tangent vector is given by the square root of the dot product of the tangent vector with itself, which we can calculate using the metric tensor for whichever coordinate system we're using. In Relativity 105b, I introduced Rindler coordinates, ct tilde and x tilde, which are a non-inertial coordinate system for an accelerating observer, with proper acceleration alpha. This observer travels on a hyperbola with a constant Minkowski distance of d equals c squared over alpha from the origin. In this part of the video, we're going to calculate the proper time along a hyperbola located at a constant proper distance of 4d from the origin. We're going to do this both in the standard inertial coordinates using the Minkowski metric and also the Rindler coordinates using the Rindler metric. And we're going to find that our result of the proper time along the curve ends up being the same in both cases. To do our calculations, I'm just going to remind you of this fundamental hyperbolic trig identity, cosh squared minus sinh squared equals 1, because we're going to be using it a lot. Also, remember that the derivative of cosh is sinh, and the derivative of sinh is cosh, which we can show easily using the exponential representations. So in the standard inertial coordinates, this hyperbolic world line is described by parametric equations. The time variable ct is equal to 4d times sinh of lambda, where again, lambda is our path parameter. And the position variable x is given by 4d times cosh of lambda. This lambda variable increases as we travel along the hyperbola, and again, lambda does not have any direct physical meaning. Remember, our goal is to calculate the tangent vector ds by d lambda. We can expand this tangent vector using multivariable chain rule and see that the components of this vector are dct by d lambda and dx by d lambda. dct by d lambda is 4d times cosh of lambda, and dx by d lambda is 4d times sinh of lambda. Plugging these in, we have a vector formula for the tangent vector ds by d lambda. When lambda is equal to 0 on the horizontal axis, sinh of 0 equals 0, and so this tangent vector is completely vertical in the time direction. If we plug in different values of lambda, we see that this tangent vector is in fact always tangent to our world line, as expected. If we plug this into ds by d lambda dotted with itself and expand, we get 4 terms. If we recall the Minkowski metric for spacetime basis vectors, et.et equals positive 1, ex.ex equals negative 1, and the cross terms go to 0. And using the fundamental hyperbolic trig identity, this simplifies to 4d all squared. If we plug in the length of the tangent vector into our proper time integral, the square root term is constant, and we can just pull it outside of the integral. And the antiderivative of d lambda is just lambda. So this becomes the final value of lambda minus the initial value of lambda. So now we have a formula for the proper time along this curved world line. This formula is basically a translation between our path parameter lambda and our proper time tau, or equivalently c times tau. It tells us how much proper time has passed on the curve between known values of lambda. For example, if the final value of lambda is positive 2 and the initial value of lambda is negative 1, plugging this into our formula, we get the total proper time c times tau along a segment of the curve is equal to 12d. Now, let's redo this same calculation of getting the proper time along this curved world line, but this time let's calculate the result in the Rindler coordinates. First, we need to convert the standard inertial coordinates ct and x into Rindler coordinates ct tilde and x tilde. We already derived the formulas for this conversion in Relativity 105 Part B. X tilde is just the positive square root of x squared minus ct squared. Plugging in these formulas and factoring out 4d and setting this to 1 by the fundamental hyperbolic trig identity, we get that x tilde is a constant value of 4d along this curve. We also know that ct tilde equals d times arctanch of ct over x. Plugging in ct and x, the 4d's cancel, and sinh over cosh becomes tanch. Since arctanch and tanch are inverse functions, they cancel out, and we just get the input argument lambda. So ct tilde equals d times lambda. So the parametric equations for this world line are a lot simpler in Rindler coordinates. Again, we need the tangent vector ds by d lambda, which equals this multivariable chain rule expansion. dct by d lambda is just d, and since x tilde is a constant, its derivative with respect to lambda is 0. Plugging these in, we get that the tangent vector is just d times et tilde, with no x component. Since et tilde is always tangent to this hyperbolic curve, it makes sense that the tangent vector ds by d lambda is just a scalar multiple of et tilde. Now, ds by d lambda dotted with itself is just d squared times et tilde dot et tilde. Now, a problem here is that we've never calculated the dot products of the Rindler basis vectors before. In other words, we don't know the Rindler metric yet. But it's not difficult to figure out. From Relativity 105C, we learned the multivariable chain rule formulas for changing from the inertial basis to the Rindler basis. So we can take et tilde dot et tilde and expand it in terms of the et and ex basis vectors. After we distribute, the et dot ex terms go to 0. And remember, et dot et equals positive 1 and ex dot ex equals negative 1. And also remember that cosh squared minus sinh squared equals 1. So we get that et tilde dot et tilde equals x tilde over d all squared, which is also x tilde times alpha over c squared all squared. It's not hard to show that et tilde dot ex tilde is 0 and ex tilde dot ex tilde is negative 1. Now that we have the Rindler metric, which lets us calculate the lengths of vectors in the Rindler basis, let's go back to calculating the length of ds by d lambda in Rindler coordinates. This dot product of basis vectors is x tilde over d squared. These d squareds cancel and we just get x tilde squared. But remember, on our world line in this example, x tilde is just equal to the constant value of 4d. So the dot product of the tangent vector with itself is 4d all squared, which is exactly what we got last time in the standard inertial coordinates. This means that our formula for the proper time along our world line is the exact same as before. C times tau equals 4d times the final value of lambda minus the initial value of lambda. Again, if the final value of lambda is plus 2 and the initial value of lambda is negative 1, plugging this into our formula, we get that the total proper time, c times tau, along this segment of the curve is 12d. So we've shown that the proper time along a curve is the same whether we measure it in an inertial coordinate system or the non-inertial Rindler coordinate system. But this fact is not surprising, because the proper time along curves is just a result of this arc length integral with this tangent vector. And the tangent vector is an invariant 4 vector, which doesn't depend on any coordinates at all. We can expand the tangent vector in terms of different bases, using multivariable chain rule, and get different components for it, but the tangent vector itself is invariant and unchanging. And that means that the Minkowski length of the tangent vector, which is the square root of the vector's dot product with itself, is also an invariant quantity. And here's one last fact. When integrating over the path parameter lambda, we got a relationship between lambda and the proper time along the path. But as I said before, the path parameter we choose for the integral doesn't matter. If I change the path parameter to the Rindler time ct tilde, it's possible to get a relationship between the proper time c times tau and the Rindler time ct tilde along Rindler hyperbolas with constant x tilde. If we compute this integral, remembering the Rindler metric and that the x tilde coordinate is constant, then we get that the proper time along a curve of constant x tilde is x tilde over d times the final time minus the initial time. If we assume that the starting time is 0, we just get x tilde over d times ct tilde. This formally proves what we assumed in Relativity 105 Part B. The proper time c times tau along a hyperbola in Rindler coordinates is not equal to the coordinate time ct tilde. They are only the same in the special case of x tilde equals d. Otherwise, the clocks with larger x tilde values will tick more quickly, because they get more proper time for a single unit of t tilde. The reason for the faster ticking clocks to the right is because the et tilde basis vector gets longer and longer for large x tilde. So the et tilde dot et tilde component of the Rindler metric grows to the right. This tells us that when the time basis vector is longer, it indicates a clock that ticks more quickly along a coordinate curve of constant position in that coordinate system. To summarize this video, I explained that the twin paradox is not a true paradox because if Alice's world line is inertial, then Bob's world line is non-inertial, and so the world lines are not equivalent. Alice's world line experiences longer proper time because a straight inertial world line always has the longest proper time between any two event points, by the reversed triangle inequality. We also showed how we can integrate a tangent vector along curved world lines to get the total proper time along that world line. And the result is the same in all coordinate systems because the tangent vectors are invariant and don't depend on the coordinate system. I also want to clear up a possible point of confusion before this video ends. In this video, I said that a straight inertial line between two event points will always have the longest possible proper time. But in previous videos, I said that the proper time is the shortest possible time between two events. Some people might be confused how these are both true at the same time. When I said the proper time is the shortest possible time between 2 points, I was talking about a clock moving in space-time along a single vector, and what happens when we measure the components of this vector in different reference frames. The time where the two events happen at the same position, the proper time, will always be the shortest of all of these times. All the other reference frames will see this time increased due to time dilation, because they see the clock moving in their frame. And in this video, when I said that a straight inertial world line between two events will always have the longest possible proper time, I was referring to looking at all possible world lines that join these two events. Each world line will have its own clock and its own proper time. The straight inertial world line will have the longest proper time of all of these world lines, because of the reversed triangle inequality for time-like vectors in space-time. The other world lines will have shorter and shorter proper times the more bent the world line is, approaching a proper time of 0 as we approach the speed of light.